Welcome back to The Explainer. Today, we're on a mission to decode the invisible architecture behind our absolute favorite apps. We're talking about those underlying structures that just make the digital world spin flawlessly. Think about it for a second. Have you ever wondered why you immediately get an error message telling you that your ideal Instagram name is already taken? Or, hey, how Amazon can keep track of millions of different orders, customers, and products without mixing up your drone delivery with someone else's socks? Well, the answer lies in the database blueprint. Okay, so let's dive into this by anchoring our entire journey to a really simple metaphor. Just like building a house requires a detailed architectural floor plan, managing massive amounts of data requires a strict, multi-level blueprint. And this is exactly what we call a database model. It's essentially a diagram that maps out a set of tables and the relationships between them. It gives us a crystal clear picture so developers don't end up with, missing data or faulty reports down the line. We've got a great roadmap for today's explainer. We're going to cover the blueprint of a database, then the ER diagram components, followed by data relationships, and finally, wrap things up with cardinality and primary keys. All right, let's jump right into Section 1, the blueprint of a database and its structural phases. When a data model is being designed, it stair-steps us from a highly abstract, kind of pen and paper idea all the way down to a concrete, machine-readable format. It basically progresses through three main stages. First, we have the conceptual model, which defines what the system contains. Next, the logical model defines how the system should be implemented. And finally, the physical model dictates how data is actually stored on the physical computer. Let's move into the second phase and see how this builds. This is the logical data model. It zooms in on our blueprint by adding what we call attributes to our entities. So take the student entity, for example. Instead of just a generic label, we now know exactly what details a student contains. Things like student ID, first name, and email. It's highly detailed, but the cool thing is it remains database agnostic, meaning it doesn't tie us down to any specific software just yet. Now, the absolutely crucial point here is that when we cross into that final physical stage, our architect terminology literally transforms into engineer terminology. Those abstract entities become concrete tables, and the descriptive attributes become structural columns. We are officially shifting from a neat concept to actual workable database code. And this brilliantly illustrates that physical model. Notice the difference? We've dropped the spaces in our names, mainly because spaces make writing database queries a total nightmare. But even more importantly, we've assigned strict data types, like varchar for variable strings of text or integer for numbers. This tells the specific database management system exactly what kind of data is expected and how to safely store it on the hard drive. Moving right along to Section 2, the ER diagram components, our core building blocks. Think of an entity as a noun, a person, place, or thing that we actually want to track in our database. In an ER diagram, an entity, like a student or college, is always drawn as a sturdy rectangle. This is fundamentally your core building block. Zooming in further on our entities, we have attributes, which are drawn as ovals. If you notice a key attribute labeled with something like roll number, you'll see it's underlined. Well, that underline is a universal symbol telling us that this specific trait uniquely identifies that student among all the others in the entire database. But hey, data isn't always simple, is it? Sometimes a trait is pretty complex. Take an address, for example. It becomes what we call a composite attribute. See how it branches out from one oval into smaller, distinct sub-attributes, like PIN, state, and country? It's just a perfect way to keep all that granular data flawlessly organized. Now, this next one is really fascinating, the dashed oval. This represents a derived attribute. A perfect example here is age. We don't need to manually update a student's age every single year, right? Instead, it's a dynamic value that's automatically calculated or derived from another attribute entirely, like their date of birth. That brings us to Section 3, data relationships. Let's start connecting this data together. Relationships are represented as diamond shapes connecting our rectangles, and they come in 4 distinct flavors depending on exactly how the data overlaps. We've got one-to-one, one-to-many, many-to-one, and many-to-many. To see a many-to-one relationship in action, just look at the M and the 1 on the connecting lines. It makes the logic incredibly clear. Many different students can be enrolled in one single college, but a single student isn't attending many colleges simultaneously. It creates a highly structured, logical flow of information. And finally, Section 4, cardinality and primary keys, the rules and the locks. So cardinality might sound like some heavy industry jargon, but it simply defines the absolute minimum and maximum number of interactions using specific line notations. Those little crossfeed and circles you see on the lines, they dictate strict rules like zero or many, or one and only one. By putting these symbols on the connecting lines between a customer and an order, we create a foolproof rule. Think about it logically for a second. A customer might register for a site but place 0 orders, or, hey, they might place dozens. So we use the zero or many notation. But an order? For an order to even exist in the system, it absolutely must belong to one and only one customer. Finally, to lock all of this data in place physically, we use primary keys. A primary key is basically a minimal set of columns that uniquely identifies every single row, or tuple, in a table. This is exactly what establishes those unbreakable relationships and prevents the whole system from confusing two completely different pieces of data. Let's look at this in practice. In this example, we have student ID, name, and age. Now, obviously, multiple students can be named Mark. Multiple students can be 17 years old. So neither of those columns can be the key. Only the unique student ID column can serve as the primary key to perfectly identify each record. This is exactly why you get an error if you try to pick an Instagram username someone else already has, because that username is acting as a unique key in their massive database. I want to leave you with a pretty provocative thought. If your favorite app's database blueprint just completely collapsed today, what would happen to your digital identity tomorrow? Seriously, every post, every order, every message you send relies entirely on these invisible, beautifully structured data blueprints. So the next time you open an app, try to picture the entities, relationships, and keys interacting underneath it all. Thank you so much for joining me on this explainer, and definitely keep exploring the fascinating systems all around you.